So what is interpolation? It is when I do experiment or simulation, I get results for some finite number of points. Okay, for example, temperature, I may not record every second, in fact nobody records every second unless you are doing some experiment related to which requires 1 second, normally required per 15 minutes, but sometimes I may require temperature in between, or I want to forecast for temperature tomorrow. So that is called interpolation. Interpolation is general word, is also used for extrapolation, tomorrow's temperature. So we are given, so I am going to denote my variables as xi, this is my independent variable like time for example, and this is my function value at xi. Okay, so this is a dependent variable and we get some n points, and using these n points I should be able to interpolate any value in between. It was very useful. So for even mathematical calculations in the past, so the person we will discuss Lagrange in this class, but there are other people also involved in this procedure, in this game. Hermite interpolation is also very important interpolation, but I will not do in the class. But all these guys were really wanting very efficient interpolation scheme. The reason being any function, for example sin x, I need sin x for my trajectory of planets, no. So you need for particular phi, which could be in seconds or minutes. So they will interpolate accurately. So for that reason it was very important problem which was of interest to a lot of very famous mathematicians, physicists in the past. Now with computer we are lazy and we make computers do all this task, but they are doing by hand 500 years back, 400 years back. So I am going to cover Lagrange interpolation. And the same Lagrange of mechanics. So the idea is quite simple. So suppose I have 2 so let us first understand for 2 points the formula, how we can write this interpolation. So I am going to draw this x axis, y axis. So I am going to call them x0 and x1, right, by following this notation, and value of the function is y0 and y1. y0, y1. Now I may want value of the function anywhere in between for this x or this x or outside. So I need a formula. Okay. So for 2 points is easy, linear interpolation. So I just make the function which is linear. Well, I do not have the choice, I do not have any other point. So linear interpolation is a valid interpolation, or in fact only available interpolation with 2 points. So now the way to write this in a very systematic or very transparent manner is, so play attention, so how am I going to write? So x, so I am going to write like x minus, so x minus x0. So now if I put x1, I should get y1. So this is, so well of course you can make a linear function, no, passing through these 2 points, but I want to kind of automate this for more points. So this is linear in x, it satisfies the value of the function at the condition I need to demand is the function I am going to write is, well let me just make another remark, the function which is really the function like temperature for example passing through these 2 points is f of x, but I do not know that function, I really do not have access to that function, but I am approximating this by a polynomial, and is a polynomial. Okay. So, what I am writing is P1 of x. So, first order, actually P2 of x, second order, first order polynomial involving 2 points. Now, this is one of them. So, what should be other point? So, should be x1 minus y. So, this is the function, and this is not the actual function, because the actual function I do not know, and we call it P2 of x. Okay. So, this is the first order polynomial going through the 2 points. Now, we can easily see what are the properties of this function, that P2 at x0 should be, if I put x equal to x0, this becomes 1, y 0, and this is 0, right. P2 of x1, y1. So, that is satisfied. Now, this part, this function, we call it L0 and L1, L1. Now, let us generalize it to n points. Now, this motivation is clear how we write the function. Now, I want to write for n points. So, my points are xi to xi comma yi. I goes from 0 to n minus 1. So, if following Python notation, so its index starts from 0. So, the idea to write this function, so we write this Pn of x as it involves lots of points. So, I am going to write this as y of j sum Lj of x. So, j is one of the indices, and j goes from 0 to n minus 1. Now, Lj is written quite nicely as a Lj of x is a product function. So, product. So, in very similar fashion, so this is x is here, x I j. So, this is a product. So, is this product over all i's except I equal to j. When I equal to j, this will blow up. I, but I not equal to j. Okay. So, how many of these I will get? For every point I will get one polynomial, and there are, this involves n minus 1 product. So, this is of n minus 1th order polynomial. Now, does it satisfy a relation like this? So, let us look at Pn of xk. Pn of xk. So, for which one it will be non-zero? So, xk is one of these points. Huh? So, in the top it will become 0 if, so the one which will not be 0 is when involving j equal to k, because that will not have xk here in the product. So, this is all these points except one point. So, x minus x0, x minus x1 all the way up to that except one point. So, if xk is involved in any of these products, so there are in fact n of them, there will be 0. The one which is non-zero is where xk is not there, and then in fact that becomes 1. So, this function will just give you y of k, because this Lj of xk satisfies the property delta function, delta jk. Okay. So, So, this is a very useful function, and your polynomial, required polynomial, which Lagrange provides us, is this. Now, using this we can interpolate to whatever x you like. Of course, for some x the error is more, for some x error is less. Now, how do I estimate error for this function? Now, somebody gave you the answer, but now we should be able to get the error. So, estimating error is not a, I mean I will do full mathematical derivation for this. What is the error estimate for this, which I will not do it for lot of other algorithms, but for this I will show you how to estimate the error, and it is done by using Rowe's theorem. So, this is part of your analysis, no, first year or so we will use Rowe's theorem to get an estimate on the error. So, I will do well, I will do little bit slowly. I will also prove Taylor's theorem, okay, for the, which is not exactly related to this, but I will prove Taylor's theorem, and that will be springboard for analyzing error for Lagrange polynomial. So, is the Lagrange polynomial clear? So, this is my interpolated function. Okay, so we are going to take a detour. So, detour is to first get error for Taylor's theorem. Now, Taylor theorem is just Taylor series, and Taylor series is written in slightly mathematical manner, which involves error as well. So, first we need to Rowe's theorem. What is Rowe's theorem? So, suppose I have a function which is 0 at 2 points, is 0 at point A and point B, then I can claim is a continuous function and differentiable function. They can claim that there exists a point C. So, there are a lot of symbols in mathematics. So, please remember this is a product, like series, this like everybody knows this symbol, product. So, this involves, so let me just write this. So, the symbol is very critical. So, if I have 3 points, then I will have term like x minus x0, x minus x1. So, this is product. Now, I have the symbol called there exists. So, this is shorthand. So, there exists C such that f prime, the derivative at C is 0. So, there is a point, in fact the point is here, and where it will be 0. Okay. Now, this can be generalized when, so I assume that f a is 0 and f b is 0, but it need not be 0 for some other function. So, it has value f a and f b, then whatever function it may be there, they can get, there exists at least one point, there exists a point C such that f prime C, this is called mean value theorem, okay. And what is that? So, this is A and this is B. So, f b minus f a divided by b. So, there exists a point C, I do not know where that point is, but there is a point C, okay, and this will need to prove our error estimate, or well, get a formula for error estimate. I would not say prove, get a formula for error estimate. The Taylor series is also useful for our course as well, but this is part of the analysis, but I am going to redo this thing. So, again in mathematics you will say a lot of mathematical symbols. So, there is a interval a b, okay. So, interval a b. Now, I want to get value at any point x. So, Taylor series, you know that I do near a point x0, okay, there is some point x0. and about which we expand, right. So, that is Taylor expansion. So, we write f of x is f of x 0 plus f prime like this, and this goes up to higher order terms. Now, the real Taylor statement is, so the function is continuous between a and b. So, let me just write this statement. So, now this is not the acceptance Taylor, it is only approximate statement of Taylor. What Taylor says is that function is continuous between a and b, and it is differentiable to n plus 1th order. So, you can differentiate that many times, this function. Then we say that there exists and of course, the interval. So, I will choose a point x 0, which is the point about which I am going to expand. Then it says which x naught belongs to a b, and let me just get this. So, I am going to write this here. Then for every x belonging to a b, there exists a zeta x between x naught and x such that f x is, so this is my real function, but I am approximating this by a polynomial p n of x, nth order polynomial, plus a remainder. This is a remainder. And so, this formula for both of them. So, p n of x is, so f x is not written like this, in fact this is p n of x. So, this p n of x is here, and the last term of this is a nth order polynomial, sorry n minus 1th order polynomial. So, this is n minus 1 x 0 divided by n minus 1 factorial x minus x 0 n minus 1. Okay. So, this is a polynomial of the order, highest power is n minus 1, and what is the remainder? This one, this guy is 1 by n factorial f n zeta of x So, this zeta of x is coming here, that point, there exists a point. So, you should take the derivative, nth order derivative at zeta x, not at x. Okay. So, this is exact relation. Now, problem is, of course, you do not know what is zeta x. There exists does not mean that I know where it is, okay. But we can make a bound on that. So, I can say that, well, this number lies between a window, and that will give a bound on the error. So, that is what you can say, you cannot quite figure out most of the time what is zeta x. So, shall we do the proof? You have done in your math course, one math proof I would like to do. My function f x, which I do not know, I am approximating it by a polynomial and a remainder, and polynomial is that Taylor series that we use, but there is a something which is an error. An error will be of this form, and zeta x lies between zeta x lies between x naught and x. So, if I draw this, so A is here, B is here, x naught is here, x is here, and my zeta will be somewhere here, zeta, and that will be a function of x. There is a problem. For every x, zeta x will be different. Okay. So, the proof So, I have to look at this notes. So, construct a new function g of t which is f x minus x of t. So, instead of x 0 I put t, okay, it will become clear why I am using t, minus x minus t by x minus x 0 to the power n f x minus p n. So, this is my function. So, x naught x, so I am focusing on this region and my point t is somewhere here. In fact, I want t to be zeta. Okay. Now, what is the value of g of x 0? So, at x equal x 0, this becomes 1 and this becomes f x 0 and so it is 0. What about g of x? So, I make it, so this is 0, okay. So, t of x 0 and here g of, so p of x x is same as p, so x equal to x 0, so that is f of x, right. So, that is f of x by definition, so that is 0. So, I can use Rolle's theorem now. So, at these 2 points my value of g of t is 0. So, use Rolle's theorem and seeing that there exists a point C where the derivative of g prime is 0. I will call it zeta instead of c. So, there exists a point zeta where g prime zeta is 0. So, now, so instead of t I have to substitute zeta and take the derivative. So, I will get f prime of x. So, I have to take derivative with relative to t. Okay, so this is not there. So, p n prime x, so this with relative to t is zeta equal to, so this should be 0, so I am going to take it right hand side. So, take the derivative of this with relative to t. So, that will be n x minus t n minus 1 divided by x minus x 0 to the power n. Actually, let us put this plus sign here. So, this minus minus gives you plus. So, f x, so nothing happens to this, no, p n x comma x 0, this is equal to 0. Now, what is this? So, let me write this as d by dt and I substitute t equal to zeta. Now, what is this object? So, my p n is here. I have to take with related to, so the p has 2 arguments. So, right now I did not write it, it was x 0, around which point are you doing it? Now, instead of x 0 I do t and take the derivative. So, if I take the derivative, what will I get? So, let us just look at few terms. So, d by dt of x comma t. So, this is f prime. So, instead of x 0 you should put t. So, f prime of t plus, now this is going to be f double prime of t x minus x 0 plus product rule. So, this is f prime x t and derivative of this, so that gives you minus and this will cancel. So, lot of this cancellation will take place. So, f double prime will cancel with the next term and all the way, and finally we are left with derivative of this. So, this part you do it as homework, okay. So, just do it at home. So, this term when I do all that analysis comes out to be f n zeta by n minus 1 factorial x minus zeta to the power n minus 1. Okay, so, this is a derivative at zeta. Now, did I miss a minus sign? I think it is okay, right? There is a minus sign here, there is a minus sign here. Okay, this one has a minus sign, this is a minus sign, this is a minus sign. Okay, so that now is fine. So, do the homework and you will get a minus sign here, plus this equal to 0. This is okay. Now, this is not a simple proof. Of course, this is that is why Taylor series is famous, but now you can find out what is the error. No? So, where is the error? This is the error, right. So, what is the formula for error? So, error here this E. Now, this I have to take it to the left hand side. Error equal to, so there will be cancellation. So, this T, okay. So, this will cancel with this, right, this is exactly same term. Now, this will go to the left. So, this error is f n zeta x minus x naught to the power n. Now, this is already n minus 1 factorial and the n will come n factorial. So, this is error, and I know the zeta lies between x0 and x. Okay. So, this is a proof. Okay, this is how you Taylor proved it, that there is a Taylor series, but there is an error, and error is like this. Okay, understood? Lost. And I send these notes, just do it once more, and this is just using this Rose theorem, you can prove it. Okay, now let us apply this to Lagrange interpolation. Okay, so I have to construct new G of t. This won't work, this for Taylor series. On the same idea, but you use the new G of t. The new G of t, so I am going to erase this part. So, it is quite similar. I have to copy this, I do not remember this formula. So, the polynomial we already have written. So, what is the polynomial? Let us write the polynomial. I need this polynomial. Pn of x is the product x minus xi y. Okay. So, this my polynomial which I am approximating, using which I am approximating function. So, this is my polynomial. So, I am just going to write this as p of t. Now, f x minus, so this is p of x, no x0, I am not expanding around any x0, and this function is replaced by product p minus xi x minus xi, and this product for all i's. There is no division by 0 problem now, all n points. Okay, this is my G of t. Now, this G of t is 0 at many places. Okay, so is 0 at, what about G t equal to xi's? So, if you put 2 equal to xi, this is 1. So, this becomes equal, right, fx minus p n t. So, is 0 at all xi's, and how many of xi's are there? N of them. So, is 0 at n points. So, if I make this line at all these points x0 this function is 0. What about g of x equal to, they put this equal to x, so this again is 1. Okay, did I make a mistake? No, I did it, I did, okay. So this is 1 and this is 0, this equal to that 0. So I think I did make a mistake. So at t equal to xi this is 0 and f of x equal to Pn of xi. So that's, so it is 0 at all these points. Actually I made a mistake, another mistake, f of t, sorry, that was a mistake. Okay, is it clear? So at xi's this is 0 and this equal to that, sorry, this is anyway 0, this equal to this at xi's. At those points a function, value of the function equal to polynomial, value of the polynomial, and at t equal to x this matches with that. Okay. So there are n plus 1 points where my g of t is 0. So now apply Rolle's theorem how many times? I keep applying n times. So first time I get polynomial n minus 1th order polynomial, there are n zeros, not n plus 1, n zeros. So keep going down and you take derivative n times, and then I can claim that after nth derivative there is a point zeta such that g in theta is 0. Okay, is that clear? So apply this Rolle's theorem again and again and again till you see there are 2 points. So finally I will see that g of n minus 1 of x of t is 0 at 2 points. We do not know which where are the points, but I say 0 2 points, and then I say that my derivative will be 0, the next derivative at some point in between that 2 points. Okay. So now I have to set this to 0 and now take the nth derivative, nth order derivative. Now it's a bit of task, but it will come out quite simple after this. So if I take the derivatives, let us see. So I will take with relative to t. Okay. So I will get fn of zeta minus pn of zeta. I can see that a lot of you are not enjoying it. Now take the derivative of nth derivative of this. So this is order t to the power n, right, is nth order polynomial. So highest power is t to the power n, and any other power, lower power will be 0. So this is going to be n factorial divided by the product x minus xi is 0. Now this Pn, so the P is of what order? This P of t, n minus 1th order. Highest power is n minus 1. So this is 0. So now I have the error, no? So what is the error? So this is my error. So error equal to fn of zeta product x minus xi by n factor. Okay. So it's not very difficult, but you just have to go through this several steps. Okay, so let's do some examples. So I am going to illustrate one simple example first for Taylor series. how to estimate error. So, Taylor series, I will just do it first, then I am going to run this Python code and I will just show it here. So, let us do e to the power x. Now, I am going to expand near 0. So, my x equal to x0 equal to, so 0. So, Taylor series is for, so let us keep only 3 terms. So, first term will be, so this 1 plus x, so everybody knows that x divided by 2 plus error r. Now, let us try to estimate value of the function e to the power 1. So, what is according to this, what is the value without error? If I do not worry about the error, 1 plus 1 plus half 2.5. Now, how do I estimate the error? So, I have to see this error. So, can I get an estimate of this? So, my error is 1 by n factorial. So, I have done up to 2. So, n should be this 2 factorial, no? N is 2, so I have to do 2 factorial. Is it 2 or 3? 3. So, it should be 3 factorial, no? So, this is, I am gone up to, so yeah, so I have gone up to squared, so that this is third factorial, x minus x0 squared. So, next is x minus x0 cube. So, 3 factorial, derivative, nth order derivative. So, it is going to be just e to the power x, but the at point zeta, which lies between 0 and 1. So, zeta is somewhere here, x to the power n will be x cube, but x is 1. So, this becomes 1. Now, I get something e to the power zeta by factorial 3. So, what should I do with it? So, I make a bound on this. So, what is the maximum value of e? So, I have to say, well, this function zeta, well, zeta could be close to 0 or close to 1, anywhere. So, I have to just estimate from here. If it is close to 0, then value of the e is 1 by 3 factorial 1 6. E near 0, if zeta is near 0. What if e is around 1? So, e by factorial 3. So, that will give you e by 6. So, my function is bound, am I getting it right? So, my function is bound between, so well, this is bigger value. So, yeah, I have put a bound, my error is lying between 1 by 6 to e by 6. Am I making a mistake? That seems correct. So, 0.1, okay, so this is correct. So, this is yeah, so if you put it right, it is correct. So, e is 2.71, yeah. So, these are lower bound. So, e is, well, I mean, just to get this thing right, e lies between 2.5 plus 1/6 and 2.5 plus e by 6. Now, of course, this is a trivial problem where I can get this bound quite easily, but you can also get this, I mean, if you do it carefully, you can get the bound. I mean, this is not a big problem. Okay. Now, let us do, I have something like 7 minutes. So, let us quickly do one problem with Legendre polynomial. Let me just first, without going through the code, I can run the code very easily. So, I am taking 1 by x an example, 1 by x is a function. So, this is for illustration that I suppose I know the function 1 is 1 by x. Now, I take several options. So, I take 2 points. So, please remember, so 3 4 I am computing. So, I am going to construct a function using 2 points, 3 points, 4 points, that is what I will do. So, here the blue curve is using points 3 and 4. Okay. So, at point x equal to 3 I get value 1/3, which is here, 1/3 is here, 1/3 here, okay. And at point 4 I get 1/4, which is here. Is that clear to all of you? So, I take these 2 points and I have 2 values, 1/3 and 1/4. Now, well, I mean I have given only these 2 values and I make an interpolation. Now, well, suppose you do not know what this function f of x is, but I given these 2 points, I can make interpolation and that will be a straight line, the blue line. So, there is a straight line which is the first order polynomial P2. Now, somebody says, well, I will give you more points. So, I will give you points values at 2, 3, 4. So, 2, 3, 4 is, I give the value at 2, which is 1/2, which is 0.5, 3 and 4. Now, there is a line going through that, a line going through is pink, the pink line, okay, which is kind of, so 1/x is white line, the real line is one white line, and my interpolation with 3 points is doing quite well, right. I mean, we agree with that. The pink line and white line are quite close. I can also do interpolation with 3, 4, 5. So, 3, 4, 5 instead of using 2 I can use 3, 4, 5. So, that is a yellow line, yellow line is also doing reasonably well. Pink line is off here and yellow line is off here. So, interpolation is good for the points in between those points given to you. Extrapolation is always bad, and the reason is because of this product x minus xi. If your x is outside this region of xi's, that means lower than minimum of xi's or higher than maximum of xi's, you will get more error. So, you have to be careful. Interpolation is good, extrapolation is not so good. Now, if I use 4 points, which is red or a light red brick color, which is fitting well all the way, okay, in this band. So, fourth order is because I am using 4 points, I can get cubic order accuracy. It is a polynomial, so I am able to approximate my function 1/x by a cubic order function. So, this is how I will show you the code in 1 minute. Now, error. So, these are the error for those 4 polynomials. Error, you can see that for 2 points is bad, lot of error. I am putting with sign. I really should put absolute if you like, but I am putting with sign. It is not good. Yellow is not good in this regime and the pink is not good in that regime, but red is good all the way. So, this is telling you the error. This error was computed by, I know the real answer minus what Lagrangian polynomial gives me. I did not use this formula because I do not know what zeta is. So, I cheated. I mean, I am getting error from the exact value, and these are the value of the function. Now, here min max I applied these ideas. I am now putting a bound. So, now I know the derivative, since I know the function f of x. In fact, if you do not know the function, then derivative calculation itself is the tricky part, no? How will you compute the estimate of the derivative? But I know the function, so this is the table which tells you that this is the value of the function. Error is decreasing. So, my error is always between these 2 bounds. At the midpoint is not, none of them are doing so badly though. This is the value of the function at 3.5, and 3.5 all of them are doing reasonably well. I mean, the difference is not so much because it is just lying in between the 3 and 4. Okay, so let us look at the code quickly. Okay, now it is probably too tiny for you to see. So, this is the loop. Now, Lagrange interpolate given the x array and y array. So, I give the array x, so this is set of xi's and that is set of yi's, and I have to give the value of x where I want to interpolate. So, this will give a number, it returns answer. Now, this is denominator xi minus xj minus xi, remember xj minus xi, and this is numerator j not equal to y. One is product, other one is a sum. So here this is a product, this one. Now the outside is a sum. I am summing over all j's, so all yj, remember. So this is the formula I am using. So quickly yj sum Lj of x. So this part is Lj, this will give me Lj, and then I have to sum over I, sum over j. So sum over j. So please use index. I and j are reserved for loop indices, and this will do the work. To estimate error, I have put this product function, which is x minus xi. So I put some comment here. Okay. So this one does the job, and this is how I generated those plots. So for 2 points, it's easy. So my x array is 3, 4, y array is 1 by 3, 1 by 4. My answer is 1 by 3.5. I am estimated at 3.5. So I can estimate by Lagrange interpolate that function. So I should use function for this, because I can reuse it all the time, and my answer is estimate, and test x is 3.5. Okay. So this gives me that stuff. So it's easy, I can do with any point. So I will leave this code, but you should be able to write this code. We can also do it for 2 dimensions. So this is interpolation in 1D. It's easy, but I mean you have to again. So all these schemes, it may look too simple or it may look too complicated. You have to just stare at it once more and code it yourself. Write your own program, and then you will understand it. Okay. So I will stop.